I started counting the countries where people died from the 1960 Valdivia earthquake. Not from the shaking, from the tsunami it sent across the Pacific afterward. I counted 7. The earthquake happened in southern Chile at 15 minutes past 11 in the morning on May 22nd. The last deaths occurred in Japan 22 hours later and 17,000 kilometers away. I have not found another seismic event in the recorded history of this planet where a single rupture killed people on that many separate coastlines in a single calendar day. First thing in the file, the figure 9.5, which is what every reference to this earthquake now carries as its magnitude, was not known on the day it happened. It could not have been. The instruments that existed in 1960 to measure earthquakes were operating on a scale developed by Charles Richter in 1935, calibrated against events up to a certain size, with no meaningful ceiling above roughly magnitude 8.5. I pulled the original Richter scale specifications and read the section on saturation, the point at which the instrument stops distinguishing between events and begins reporting the same number regardless of how much larger the actual shaking is. Valdivia hit that limit within the first 2 minutes of rupturing. Every seismograph station on the planet that was pointed at South America that morning hit the same wall. Second thing in the file, the magnitude figure that now appears on every reference to this event was calculated retroactively, using a method that didn't exist in 1960. It was derived from Earth's own response to the strike, something the geophysical literature calls free oscillations. I had to look that up properly before I could explain it. In plain terms, when a rupture of sufficient scale strikes the planet, the entire Earth doesn't just shake locally. It begins to vibrate at its own natural resonant frequencies, the way a bell continues to ring long after the hammer hits. Different frequencies correspond to different modes of oscillation. The planet breathing in and out slightly, twisting, flexing along its diameter. Those oscillations, recorded at stations worldwide in the days after May 22nd, gave seismologists a way to work backward to the scale of what had caused them. The answer, calculated years later using that data, was 9.5, the record magnitude. The instruments in active use on the morning of the earthquake had produced nothing useful. They had run out of scale. So the Richter scale explains why a real-time measurement existed at all. What it doesn't explain is what it meant that the measurement system had a hard ceiling, and that May 22, 1960 was the morning the planet founded. I cross-referenced the station reports from seismograph networks in Pasadena, Uppsala, and Göttingen. All three show the same thing. The trace climbs, hits the physical edge of the recording drum, and stays there. Not a malfunction. The maximum the instrument could register. Whatever was happening in Chile was beyond the scale's capacity to describe. You'd assume a planet that generates earthquakes routinely would have instruments sized to measure the largest ones. The specific problem this case opens on is what happens in the hours after an event exceeds every available measurement, when the agencies responsible for issuing tsunami warnings are working from instruments that have gone flat, and the waves are already crossing the ocean. So here's the actual question. Not how large the Valdivia earthquake was, because that has since been established. The question is what the distance between real-time measurement and retroactive calculation cost. How many decisions in the hours after the rupture were made against a number nobody actually had yet? And what that distance says about every subsequent event where the same problem nearly applied. There are 2 documents in this file I'm holding back. Both describe the same morning. They look nothing alike. If the limit Valdivia found in 1960 is a structural feature of how we measure seismic events rather than a one-time failure, then every magnitude figure in use today carries a footnote. The scale that produced it was built after the earthquake that proved the previous scale was insufficient. The morning of May 22, 1960, did not begin with the largest earthquake ever recorded. It began with the second largest event of that week. The day before, on May 21st, a magnitude 7.9 earthquake had struck the same stretch of the Chilean coast. A 7.9 is by any measure outside of what followed it, a catastrophe in its own right. It is large enough to collapse buildings, trigger landslides, and kill. It did all three along the coast of southern Chile on May 21st. I traced the damage reports from the foreshock through the Chilean Emergency Services records available in international archives. The 7.9 caused significant structural damage in Concepcion, Lebu, and the surrounding coastal towns. It forced people outdoors. It drove the population into streets and open ground, and away from buildings that were already cracked and partially down. By the evening of May 21st, a significant portion of the population in the most heavily affected zones was camping outside, sheltering in open spaces, or had moved away from structures they no longer trusted. They were, without knowing it, in a less lethal position for what was coming. At 11:15 the following morning, the rupture that produces the record magnitude began. The shaking lasted approximately 10 minutes, long enough that people who had survived the foreshock understood immediately this was a different order of event. Long enough that people standing outdoors, which many were, had time to move further. 10 minutes deserves a moment to register properly, because most earthquake experience involves shaking that lasts seconds. The 1989 Loma Prieta earthquake in California lasted 15 seconds. The 2011 Tohoku event lasted approximately 6 minutes. At 10 minutes, the shaking in southern Chile outlasted most people's ability to remain standing, outlasted the structural tolerance of every unreinforced masonry building within hundreds of kilometers, and outlasted any initial assumption that the shaking would stop. Eyewitness accounts collected by Chilean authorities in the weeks after describe people clinging to trees, unable to walk, watching the ground move in visible waves. The rupture didn't feel like an earthquake in any experienced sense of the word. It felt like the ground had changed its fundamental behavior for a period of time that refused to end. The death toll for the main event in Chile is estimated between 1,600 and 6,000, depending on the methodology, with the range reflecting the difficulty of counting deaths from secondary effects that continued for weeks after the primary event. The foreshock data and the Chilean civil authority documentation that followed consistently suggests the population's forced displacement on May 21st kept the toll on May 22nd lower than the rupture's scale would otherwise predict. That thread doesn't close on the shaking. It closes in a valley to the northeast of Valdivia, where the earthquake triggered a massive landslide that blocked the outlet of Lake Reiniaso. I read the engineering records from what Chileans came to call the Reiniaso. The landslide deposited enough debris across the lake's outlet river that the water level in Reiniaso began rising immediately after the earthquake. The lake drained, normally, into the San Pedro River, which flowed directly into the Calle River through the city of Valdivia. With the outlet blocked, the lake level climbed at a rate that engineers calculated would, within weeks, overtop the debris dam and release the full accumulated volume in a single surge. Downstream, the population of Valdivia, already dealing with the damage from the earthquake itself, numbered close to 200,000 people in the direct flood path. Chilean government engineers, working in damaged infrastructure with equipment that had survived the rupture, spent weeks carefully cutting drainage channels into the debris dam to lower the lake level gradually, rather than letting it overtop catastrophically. The controlled release took months. the catastrophic flood didn't happen. It is one of the less documented engineering feats of the 1960s, and it sits entirely in the shadow of the seismological record. The earthquake that produced the Reiniaso is the same earthquake the seismographs couldn't read. The seismologist whose name is most directly attached to why the record magnitude exists as a number is Hiro Kanamori. Kanamori was a Japanese-American geophysicist at the California Institute of Technology, who in 1977 published the paper introducing the moment magnitude scale. The moment magnitude of an earthquake is calculated, not from the amplitude of the seismic wave recorded on a drum, but from the physical properties of the rupture itself. The area of the fault that slipped, the average distance it moved, and the rigidity of the surrounding rock. Those three values multiplied together give the seismic moment, and the seismic moment produces a magnitude with no saturation point. The scale works at any size. Kanamori used the Valdivia event as a primary calibration case for the new scale. The record magnitude is his derivation, published 17 years after the earthquake, using physical measurements collected in the field by Chilean and international survey teams. I read his 1977 paper and the subsequent analyses that refined his figures. The confidence in the 9.5 rests specifically on two measurements: approximately 800 kilometers of fault boundary that slipped, and an average displacement across that boundary of roughly 20 meters. Those are not estimated figures. They are field measurements, taken from the permanent deformation of the coast, from the changed elevations of benchmarks, and from the pattern of coastal subsidence and uplift that Lomnitz and his colleagues documented in the months after the event. The moment magnitude scale did something the Richter scale structurally could not. It made every subsequent large earthquake's magnitude a physical measurement rather than an instrument reading. When the 1964 Alaskan earthquake produced the same instrument overflow pattern that Valdivia had 4 years earlier, the post-event analysis could draw on the new methodology to produce a magnitude 9.2, a number derived from the rupture's physical geometry rather than from a drum that had flatlined. When the 2004 Indian Ocean earthquake that produced the Boxing Day tsunami was measured, the initial real-time estimate was 9.0, revised upward within days to 9.1, and then 9.3, using the seismic moment method Kanamori had developed. The retroactive revision process that took 17 years for Valdivia took days for subsequent events, and then hours as the methodology became standard and the computational tools improved. The scale the planet forced into existence in 1960 is the one that now runs in near real time. While the seismographs were producing flat lines, the Pacific was already moving. A tsunami generated by a subduction zone rupture begins the moment the seafloor displaces, and the displacement at Valdivia was without precedent in the instrumental record. I wasn't looking for the next part of this when I found it. I was checking the timing records from Pacific Tsunami Warning Center archives against wave arrival data at coastal monitoring points, and the pattern that emerged was something the warning system's designers had not fully accounted for. At the scale of the Valdivia rupture, the leading wave was not the largest one. I want to correct something I implied earlier about what happened in Hilo. The Pacific Tsunami Warning Center issued an alert. It was received in Hawaii with enough lead time before the first wave arrived that an evacuation was possible and was, in many areas, completed. The failure in Hilo was not the warning system. The warning worked. What didn't work was what happened after the first wave receded. Hilo sits in a bay that amplified the incoming wave train. The first wave arrived at approximately 2 in the morning on May 23rd, local Hawaiian time. It caused damage, confirmed the warning's accuracy, and then, as tsunamis do in a multi-wave series, it pulled back. A portion of the residents who had evacuated returned to the waterfront. The second and third waves were larger. 61 people died. I read the post-event testimony records compiled by Hawaii's Civil Defense Authority. The documentation is consistent across multiple accounts. The wave series was known to be ongoing. The warning had not been rescinded, and the deaths occurred among people who had received the warning, confirmed the first wave had arrived, and concluded the danger had passed. It had not. In Japan, the waves arrived 22 hours after the rupture, having crossed the entire Pacific. The Japanese coastline had received warning through diplomatic channels and through Japan's own meteorological agency. 142 people were killed, primarily on the Sanriku coast of northeastern Honshu and in parts of Hokkaido. The Sanriku coast carries a specific weight in this file because it is the same coastline that the 1896 Meiji Sanriku tsunami devastated, and the 1933 Showa Sanriku tsunami struck again, and the 2011 Tohoku tsunami killed nearly 20,000 people on for a third time within living memory. By 1960, the Sanriku communities had been educating their populations about tsunami behavior for decades. The 142 deaths on that coastline were largely among fishermen and harbor workers who had returned to the water after the initial warning window, without understanding that a wave series originating 17,000 kilometers away would not necessarily follow the short interval pattern of a locally generated tsunami. The interval between Valdivia waves at Japanese shores was measured in hours, not minutes. The warning period was longer than any previous Japanese tsunami experience had conditioned people to expect. The pattern across Hawaii and Japan is the same behavioral failure, compounded by the same wave series misunderstanding. The first wave arrives, recedes, and the population interprets the recession as the end of the event. It is not. The Valdivia tsunami was the first event large enough to make that failure pattern clearly visible across multiple countries simultaneously, and the documentation of it became a direct input into how tsunami public education was redesigned in both countries in the decades that followed. Quick aside, because the two documents I've been building toward are next: the seismograph trace and the Kanamori calculation, side by side. Back to the file. If you're drawn to what the planet's own record says about itself, subscribing puts more of these in front of you. The Chilean Coastal Field Survey that established the physical dimensions of the rupture was led in the months following the earthquake by a team that included the Chilean geologist Hugo Lomnitz. What Lomnitz and his colleagues documented between Arauco and Chiloé was not a consistent pattern of destruction. It was a map of permanent deformation. Sections of coastline near Valdivia had dropped by up to 2 meters, now sitting below the tide line that had marked their elevation before May 22nd. Forests of trees that had stood on dry ground before the earthquake were now standing in saltwater, killed by inundation, their dead trunks visible at low tide for years afterward as a kind of waterline marker for how much land had been permanently lost. Other sections had risen, near Isla Mocha. A maximum uplift of roughly 5.7 meters had exposed seafloor that had previously been submerged. Shellfish beds that had existed meters underwater were now sitting in open air, dying. The intertidal zone along hundreds of kilometers of coastline had moved, some of it upward and some of it downward, all of it permanently. Maps that had been accurate before May 22nd were no longer accurate on May 23rd. The Chilean Hydrographic Service spent years revising its coastal charts after the earthquake, not because the surveys had been wrong, but because the coastline itself had changed and needed to be remeasured. I measured those displacement figures against the rupture length and average slip Kanamori would later calculate. An 800-kilometer fault boundary that moved an average of 20 meters, and in some sections significantly more, represents a volume of rock displacement without parallel in the instrumental seismic record. 20 meters of lateral movement across a plate boundary is not an abstraction. It is the distance between 2 points on opposite sides of the fault zone that were 20 meters closer to each other before the earthquake than after it. At the surface, that displacement expressed itself as the coastal deformation Lomnitz measured. At depth, it expressed itself as the seafloor displacement that launched the tsunami. At distance, it expressed itself as the free oscillations that rang inside the planet for days and gave Kanamori the data to calculate the record magnitude 17 years later. The same 20 meters, read at 3 different scales, tells 3 different parts of the same story. The energy released is estimated at roughly 250 times the total energy released by all earthquakes in 1960 combined, a figure that takes a moment to sit with, because 1960 was not a quiet year seismically. The Valdivia rupture accounted for a disproportionate fraction of all the seismic energy the planet released in the entire 20th century. One event, one morning, one 10-minute rupture. Now, the 2 documents. The first is the seismograph trace from Pasadena for the period beginning at 1911 Universal Time on May 22, 1960. The trace runs normally in the minutes before the arrival. Then it climbs steeply, hits the upper boundary of the recording drum, and the line stays there, pressed against the edge of the paper, for the duration of the rupture's primary wave arrivals. There is no peak. There is no measurement. There is a flat line where a magnitude should be. The second document is Kanamori's 1977 derivation. It is a precisely reasoned calculation from physical field data, rupture length, average slip, rock rigidity, arriving at a seismic moment of 2 times 10 to the 23rd Newton meters. Converted to the moment magnitude scale, that seismic moment produces the record figure, the number that appears on every reference to Valdivia in the 65 years since is not what May 22nd produced in real time. It is what 17 years of subsequent geophysical work produced from the evidence the rupture left behind. The morning produced a flat line. The number came later. There is a separate file on this channel covering the 2011 Tohoku earthquake, a magnitude 9.0 event on the same class of subduction boundary, with a tsunami that killed nearly 20,000 people, despite a warning system that functioned, and with a magnitude that was initially underestimated in real time and revised upward after the fact. The structural parallel to Valdivia runs through both the measurement challenge at the upper end of the scale and the behavioral failure in the tsunami wave series, worth pulling after this one. Back to this case. I cross-referenced the Nazca Plate subduction boundary against the rupture history available in the geodetic and historical record. The 800-kilometer section that moved in 1960 has a documented history of repeat events. Spanish colonial records describe major tsunamis along this coast in 1575 and 1647. Those are not seismological measurements. They are descriptions of inundation, water heights, and community destruction recorded by missionaries and administrators. They are the only calibration data available for what the boundary did before instruments existed to record it. The sections of the same boundary north of the 1960 rupture zone show accumulated strain in the GPS and satellite geodetic data that has not been released in a major rupture since before instrumental seismology began. The boundary north of the 1960 rupture includes the section offshore Peru and northern Chile, a zone that last produced major ruptures in the 19th century. I traced the geodetic measurements available in the published literature from monitoring networks maintained by the Chilean and Peruvian seismological institutes. The numbers show continuing convergence between the Nazca and South American plates, the oceanic plate moving eastward and downward at a rate of roughly 7 to 8 centimeters per year. Strain that accumulates at that rate against a locked boundary section doesn't dissipate. It stores. A segment that hasn't fully ruptured in over a century, on a boundary that produced the record event when it last moved at full scale, is not a theoretical risk category. It is a measured accumulation of unreleased energy on a mechanism whose behavior May 22, 1960, has already demonstrated in the clearest possible terms. So where does that leave the file? Confirmed, on the physical and documentary record, a magnitude 9.5 earthquake struck offshore Valdivia, Chile, on May 22, 1960. The rupture lasted approximately 10 minutes and displaced roughly 800 kilometers of the Nazca South American plate boundary by an average of 20 meters. The resulting tsunami killed 61 people in Hilo, Hawaii, 142 in Japan, 32 in the Philippines, and between 1,600 and 6,000 in Chile. Every seismograph station monitoring South America that morning recorded instrument overflow rather than a measurement. The magnitude figure was calculated by Hiru Kanamori in 1977 from physical field data and has remained stable across all subsequent independent analyses. All of this is confirmed. What is theorized, with genuine and ongoing support in the seismological literature, is the precise geometry of the rupture. The 800-kilometer figure and the 20-meter average slip are stable across most recalculations using modern geodetic data. Some analyses place the rupture extent closer to 1,000 kilometers, with implications for the total seismic moment and the magnitude estimate's upper bound. The 9.5 is the consensus figure. It is not universally agreed to be the final word. What is genuinely unresolved is the strain state of the Nazca South American boundary north of the 1960 rupture zone. Geodetic measurements confirm accumulated strain. The historical record suggests a long recurrence interval. What the record cannot close is the specific magnitude and timing of the release that accumulated strain will eventually produce. What I believe, having read the station overflow records, Kanamori's derivation, the Chilean field survey data, the Hilo civil defense documentation, and the Nazca boundary geodetic analyses, is this. The 9.5 is a real number, carefully derived, representing a real event. The flat seismograph trace is also a real document. The distance between them is not a failure of science. The science closed the gap over 17 years. The distance is a clock, and within that clock, every earthquake that approached the same scale in the interim was being measured on an instrument that had already proven it could not distinguish at the top of the range. The moment magnitude scale that now carries every significant earthquake's official figure exists because May 22, 1960, found the limit of what came before it and forced the construction of something better. The planet produced an event the instruments couldn't read. The instruments were replaced. The boundary where that event happened is still there, still accumulating strain. And the scale that would measure the next event from it is now ready. The planet has not changed its schedule. If working through a stack of unresolved files is your kind of thing, subscribing means you won't miss the next one.